Welcome, ladies and gentlemen. This is the video to get you back up to speed on how to assign oxidation numbers to individual elements in a compound. This is an important skill. It's one that I do feel tends to be very well retained from Regents chemistry, but if it's been a little while and you need a little bit of brushing up, that's what this video is for. So first of all, some the basic oxidation number rules. There are lots of oxidation number rules, but really there are only a few that you need to remember because usually they're going to be good enough for you to use to assign oxidation numbers to everything in a compound. First of all, a reminder that if you've got an atom or an atom in elemental form, its oxidation number is 0. This applies to both the monatomic and the diatomic elements. If you have H2, that's the elemental form of hydrogen, its oxidation number is 0. If you have a piece of copper that is the elemental form of copper, its oxidation number is 0. So if you have the element that's by itself, oxidation number is 0. But you need to pay attention because if you have an ion, a monatomic ion, such as Cu plus 1, copper 1 ion, then the oxidation number becomes the charge on the ion, right? Na plus, oxidation number is plus 1. Ca plus 2, oxidation number is plus 2. Typically speaking, nonmetals will usually have a negative oxidation number, but that's not necessarily always the case, especially if you have molecular compounds, in which case you'll have one nonmetal that will have positive oxidation number and the other that will have a negative. But if you have an ionic compound, the nonmetal will be getting that negative oxidation number, whereas the metal will be positive. And when we're talking about rules for nonmetals, oxygen has usually its oxidation number is -2. This is true about 99% of the time when oxygen's in a compound. There are a few exceptions. Most notable one is peroxide, hydrogen peroxide, in which case the oxygen has a -1 oxidation number. Hydrogen, but that only comes up very, very rarely. So it's really, we can, again, 99% of the time, assume that oxygen has a -2 oxidation number. Hydrogen is +1 when it's paired up either as an acid, when the H is out in front, paired with other nonmetals, or in polyatomic ions. But it's going to be -1 when it's only paired with a metal, as in the case of a metal hydride. We talked about that calcium hydride example in class. That's a great example of hydrogen having that -1 oxidation number. Hydrogen is +1. That's like 98% of the time. We're going to assign H that +1, but it is also possible for it to have a -1. Fluorine is always going to be -1. Other halogens are going to typically be -1 when they're in a binary compound, and that's a good rule to remember because that can actually get you pretty far. If you've got a halogen that's in a binary compound, meaning just 2 elements, the halogen, you can go ahead and assign the halogen the -1 oxidation number. But if your halogen is in a ternary compound or a quaternary compound, more than 2 elements, then you cannot make that assumption and you'll have to actually figure out the oxidation number on the halogen. Some of the oxidation numbers of all atoms in a neutral compound is 0. So if you've got a compound, compounds by definition do not carry a charge. Ions carry a charge, compounds don't. Add up all the oxidation numbers, take into account how many there are of each element, add them all up, they're going to equal 0. Sum of all oxidation numbers in a polyatomic ion will be equal to the overall charge on the ion. And oxidation is the loss of electrons. That will lead to an increase in the oxidation number. Reduction is the gain of electrons. That will lead to a decrease in the oxidation number because you're gaining those negative particles. So we're just going through and we're going to assign oxidation numbers here. First example, PCl3, phosphorus trichloride. Assigning oxidation numbers from the list of rules that we sort of talked about already. When I see PCl3, the first thing I think in terms of assigning oxidation numbers is that I don't have a general rule for phosphorus, but I do have a rule that can apply to chlorine, and that's the fact that halogens in a binary compound, which this is 2 elements, are going to be -1. So I can just go right ahead and assign the chlorine an oxidation number of -1. There are 3 chlorines in the compound. There is only 1 phosphorus. The overall compound does not have a charge. That means that the sum of the phosphorus plus 3 chlorines has to add together to make 0. If each chlorine is -1, then the one phosphorus has to be +3 in order to balance out the charges. And I want to be very clear, though, that oxidation numbers are not, they're not the same as having an ion or being an ion. Oxidation numbers are showing the degree of oxidation and reduction. I call them a pseudo charge. And oxidation numbers can be useful even in molecular compounds like this one, where there are no ions, when you're thinking about the structure of the compound. They're actually informative when it comes to, sometimes there are multiple ways to draw the structure of the compound, and oxidation numbers will enter into our discussion then in evaluating which drawing of the bonding is probably most accurate. That's when we talk about this +3 and -1 for things that we know are not ions. This is not an ionic compound, this is a molecular compound. Next up, we've got calcium phosphate. There are 3 elements in this compound, and we want to assign oxidation numbers to each one. Luckily, we've got rules for 2 out of the 3. First up is the calcium. Calcium is group 2. All group 2 ions have an oxidation number of +2. It goes along with their charge. We know that Ca is +2, so its oxidation number also has to be +2. Likewise, we've got oxygen. We know that oxygen 99% of the time is going to be -2. This is not an exception for oxygen. This is not peroxide, so we could just assigning it that -2. So then it comes down to the phosphorus, and here's where we just want to do a little bit of math. We've got 3 calciums distributing the 2 for the phosphate. We've got 2 phosphoruses, and we have 8 oxygens, which I'll usually do OX here to distinguish from the 0. When we add these together, we know it has to equal 0. And then you're just plugging in. You're just plugging in your assigned oxidation numbers. So knowing that the calcium is +2 and the oxygen is -2, we're going to figure out what the phosphorus has to be. So this is +6. This is -16. Has to equal 0. When you solve this, or when you get this to a certain point, you're going to see that 2p is equal to +10. So each phosphorus has to be +5. So +5 right there. Next up, SrH2. This is strontium hydride. Here is a case where we have hydrogen that's paired with a metal. And the rule, when it's just hydrogen paired with a metal and no other elements in the compound, the hydrogen has to be -1. And additionally, strontium, that's +2. That element, that ion, it's group 2. It's always going to be +2. So here's a case we're talking about when can hydrogen be -1 in a case like this, when it's paired with just a metal. Strontium is +2. There are 2 hydrogens. The hydrogens have to be canceling out the +2 from the strontium, so H has to be -1 in this case. Next up, SO2. We don't have a rule for sulfur, but we do have a rule for oxygen, so we're going to go run right ahead and assign the oxygen the -2 oxidation number. The sulfur has got to be able to cancel out 2 oxygens. Each oxygen is -2, therefore the sulfur in sulfur dioxide has an oxidation number of +4. Doing some additional examples now with some overall charges, we've got the dichromate ion. Same idea, oxygen. You see an oxygen, realistically you're going to automatically assign an oxidation number. We know that that oxygen is -2. We're trying to figure out the chromium. So 2 chromiums plus 7 oxygens has to be equal to, in this case now, the overall charge of the polyatomic ion. So this is not equal to 0, this is equal to -2. So 2 chromiums, let's see, plus, this is a -14, plugging in that we know the fact that the oxygen is -2 is equal to -2. When you solve this out, you get the chromium being +6. The sulfite ion, SO3 2-. Similarly, go ahead and assign the oxygen -2. So we know that sulfur plus 3 oxygens has to be equal to the -2 charge on the ion. Plugging in -2 for the oxygen and solving for the sulfur, we get the sulfur coming out to be +4. Just doing some math. That's a -2. Isn't that there? The ammonium ion, NH4+. Here we've got hydrogen that's paired with a nonmetal. When hydrogen is paired up with a nonmetal, we assign hydrogen a +1 oxidation number. We don't know what the nitrogen is, so nitrogen plus 4 H's has to be equal to the overall charge on the ion +1. When you plug in and you solve, the nitrogen plugging in +1 for the hydrogen here, the nitrogen has to be equal to -3 in order to get the overall +1 charge. And the last one, sodium carbonate. We've got a rule for sodium. Group 1 is always +1, same as its overall charge. And oxygen we know is going to be -2. That means that we're solving for the carbon. So I've got 2 sodiums plus 1 carbon plus 3 oxygens. There's no overall charge. This is a compound, so that add them together, it's got to equal 0. Plugging in, I've got 2 times +1 plus the carbon plus 3 times -2 equals 0. The carbon in this case is equal to +4. So there we go. That's a little bit of a refresher on assigning oxidation numbers.